So you remember our discussions in the last class. We had a little remedial lecture on type 2A string theory, M theory, the connection between these two theories. We discussed the various brains, supersymmetric brains in these theories. We showed that you could go from one to the other. We reminded ourselves that on the world volume of D brains you got Yang-Mills theory. And right at the end of the last lecture, I told you why we went through this remedial discussion. It was in order so that you would be able to understand how you could get gauge theories on the world. You could get n equals 2 4-dimensional gauge theories in the world volume of brains. And our general strategy was to put 5 brains and 4 brains stretching between them. Okay, I'm going to go over the detailed configuration one more time. But before I do that, I'll give you one more bit of background for this discussion. In class, we discussed the Seiberg-Witten solution for n equals 2 Yang-Mills theory in 4 dimensions, no matter. Now, as you can imagine, when a development as interesting as this happens, people immediately start trying to generalize it. Okay. So there are various ways in which you can imagine generalizing. You could try to generalize to more or less amounts of supersymmetry. So that's actually difficult, and each number of supersymmetries has different physics. Okay, but a milder generalization would be, well, if you could do SU2, why not SU3? Why not SU4? Why not SUN? Okay, this was a generalization that people very quickly got to. I think Argyros and somebody else very quickly got to. And another kind of generalization that people looked at was, well, if we can study n equals 2 theory, so pure n equals 2 theories without matter, let's add some hypermultiplets to it. And then also study it. So for instance, Seiberg-Witten themselves in a follow-up paper to their famous original paper looked at SU2 gauge theory with 1, 2, 3, 4 hypermultiplets. Beyond 4, it stops being asymptotically free. They looked at this theory, and there are several such generalizations. Okay, another thing that people did was to look not just at SUN, but let's say SUN1 times SUN2 with some amount of matter between them. Okay, so by the time Witten wrote this paper in 1997, a zoo of generalizations of this n equals 2 story were available. Now, what I'm going to tell you, I'm going to without giving you any real detail, I'm going to very briefly describe just structurally how one of the generalizations works. This is the simplest of them, really. It's going from SU2 to SUN. Already you will see some elements. Okay, you see, let me remind you that in the SU2 theory, the main starting idea was we have this Coulomb branch. Okay, where you can turn on the scalar field in the vector multiplet to have arbitrary values. Okay, that you turn on this complex scalar field to have arbitrary values. That continues to be true in the SUN theory. In the SU2 theory, now let's remember, in the SU2 theory, you might have thought, well, how did it happen that we had one complex U plane? Because we have 3 scalar fields, because it's in the adjoint of SU2. Each of these is a complex field, so why didn't we have 3 complex fields? And of course, the answer was gauge invariance. Right? All these three complex fields lie in a gauge orbit. They can all be rotated to each other up to one direction, magnitude, right? Up to one magnitude, not direction, right? The directions are rotation, and this is very easy to visualize because SU2 is SO3, adjoint is a vector, gauge transformations are rotations. So all vectors with the same length can be rotated to each other. That was the reason we had only one U plane. Because up to gauge transformations, there was only one complex field. Okay? How does it work in SUN? Well, in SUN, the scalar field is in the adjoint. What can you do to adjoint fields up to gauge transformations? You can diagonalize them. Because gauge transformations are U adjoint, U diagonal. Okay, so the most general SUN scalar field can be written in the form alpha 1, alpha 2, alpha n, but such that sum over alpha I is equal to 0. So now you see that SU2 was special, it had only one scalar field. Okay, SU2 was special, it had only one scalar field. Okay, but what in general in SUN we'll have n minus 1 scalar fields. So the analog of the U plane will be some n minus 1 dimensional complex. When I say n minus 1, we're talking like a mathematician, right? It's n minus 1 complex dimension.
But even there is this while, I mean.
Correct. That's a discrete thing. Doesn't affect the dimensionality. Right? Okay. So first, the number of parameters that represent your vacuum now is n minus 1 rather than one complex variable. This is clear? Okay. And once again, the problem is to find the prepotential, to find this f function as a function now of these n minus 1 complex variables. So basically what we have is instead of having one a, we have n minus 1 a's. And instead of having one a dual, remember a dual was the derivative of a with respect to each, f with respect to a, we have n minus 1 a duals. Okay? And what you want to do is, as a function of where you are on this n minus 1 dimensional plane, complex manifold, what you want to do is to find a and a dual as a function of where you are. Clear? That's the goal for an SUN there. Now, you remember that the answer that we got was obtained by associating a torus with each point on the U plane. And then we found A as some integral of something on some cycle and A dual as an integral of something else on some other cycle. They were organized such that dA by d, du divided by dA dual by du divided by dA by du was proportional to that one well-defined holomorphic one-form field. Right? You remember all that. Okay? Now you might wonder what's going on. You might wonder what will the general solution to the SUN theory be given? And, it could have gone in many ways. But it turns out, and if you think about it, it's reasonable. It turns out that the solution here is that associated with each point on this n minus 1 dimensional complex plane, there is still a complex curve. Curve because we're mathematicians, right? It's a complex surface, two-dimensional surface. Okay? There's still a complex curve, but that curve is not a torus. It has some different genus. Okay? And we can even sort of guess what the genus must be. You see, the way we got A and A dual is by integrating something over cycles that we're intersecting. Now, if we're in SU3, we need two A's and two A duals. So we should have two sets of intersecting cycles. That'll work if we're in genus 2. If we have SU4, it'll work if we're in genus 3. And so on. So if you're in SUN, you might expect, just from this very vague reasoning, you might expect to get a genus n minus 1 dimensional, genus n minus 1 complex curve. That's what people found. This paper by Argyris and whoever else, Millikan, found a genus n minus 1 curve. Okay? I won't go through it, but there were similar generalizations when you added matter. Okay? And so, one question we can ask immediately is the following. Suppose I give you a model, quantum field theory. It's n equals 2. And I ask what kind of, I've got used to the idea that I've got some sort of complex curve attached to each point in moduli space, each point in vacuum space. You may ask the question, what kind of curve is it? Okay? Then there's a second order question of how I get A and A dual from this curve, but that's actually, it's a very canonical thing by now. You just integrate some forms on these things. One question immediately is what kind of curve? Okay? This question will have a very simple and efficient answer in a very wide and general setting in what we're going to do. Is this clear? So this is why I said this. That you don't appreciate how nice this is if you think just of SU2 without matter. Okay, great. So with this in mind, let us to start with work in a generalized setting from what we talked about last time. And the generalization is a pretty small one. It's the one we've just went through in our 2-minute discussion. Let's allow for n d4 branes. N d4 branes stretching between the two 5 branes. We will later see generalizations to having more 5 branes and various other things. But right now, let's just stick to this. Okay, already we will have something, we will see something interesting. Okay, so with all this in mind, let me remind you of the setup that we already reviewed in the last class, but it's good to have it on the board again. Okay, we have our dimensions of space-time being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm following Witten's conventions. Anyway, I'm following Witten's conventions. And in the classical picture, what we're going to do is the following. In the classical picture, these are the dimensions that are in the world volume of the D4 branes and the NS5 branes. These dimensions here, okay, these dimensions here were not in the world volume of the D4 brane, but were in the world volume of the NS5 brane. This dimension was in the world volume of the D4 brane, but not in the direction of the NS5 brane. Okay? And 10 appears only when we look at M theory. Okay, 10 appears only when we look at M theory. So let's ignore that for a minute. Just in string theory, of course, these 3 directions are in the world volume of neither. So just so that your eye doesn't go to them, I'm just putting blank, right? Blank means cross for everything. Okay? What about 10? If we were thinking in yes?
5 and 6 were in the NS5 brain and 4 was in the D4 brain.
5 and 6, I'm so sorry. Let me just check what Witten does. Four branes go in the x6 direction for Witten. So today's conventions are what Witten uses, so please use this. Okay, excellent. Okay, now if we think in M theory, again in this classical limit, remember an NS5 brane is a brane at a point on the M theory set, whereas a D4 brane is an M5 brane wrapping. So if you think in M theory, we would put a tick here and a cross here. Okay? So in M theory, everything becomes democratic. There are as many ticks as crosses, as many ticks on the first line as the second line, because both were 5 branes. 6 ticks on the first line, 6 ticks on the second line. In string theory, it's not democratic. In string theory, there's 5 ticks for the D4 brane, because it's a 5-dimensional world volume, and 6 ticks for the NS5 brane, because it's a 6-dimensional world volume. You see, when we say D5 brane, we don't include time, or D4 brane, we don't include time. Okay, excellent. Now, as I discussed, I'm going to be looking at some picture that looks sort of like this. Okay? So now the first thing we're going to ask, is the following. Okay? This picture is just a picture. How does it help us understand anything? Okay? The first thing we're going to ask is the following. The first thing we're going to ask is, once we take into account quantum effects, how does this picture change? This is a classical diagram. Okay, now why do I say classical and quantum? The reason for this is, as you remember, the tension of a D4 brane is 1 over G string, whereas the tension of an NS5 brane is 1 over G string square. Okay? What this means is that the NS5 brane in the classical limit, G goes to infinity, is very very heavy compared to the D4 brane. So having a D4 brane on the NS5 brane classically does not affect the NS5 brane. Okay? Because it's a big classical object and this D4 brane is sort of tugging it a little bit. But the tug is very, very small compared to its mass, compared to its tension. Okay? So classically, it does not affect it very much. Okay? However, quantum mechanically, when we go to finite GS, this distinction blurs up. Okay? And having this D4 brane affects the position of the NS5. The NS5 brane is a dynamical object, right? Okay? Having the D4 brane on it gives it a pull. Now we can ask mathematically how this works. Okay? We can ask mathematically how this works. So, we can ask the following. First, what can we say about the equation of motion of the NS5 brane? Let's work first at small coupling. What can we say about the equation of motion of this NS5 brane? So the equation that governs the world volume of the NS5 brane, when it's not fluctuating very much. All branes have an action that starts off as the area and then there are other corrections. Now, what is the area? The area is the determinant of the induced metric on this rippling brane. This is the area of this brane. Now suppose this brane is more or less flat. So we work with these static coordinates, meaning we work with world volume coordinates being the spatial coordinates in the direction 0, 1, 2, 3, 4, 5 of the NS5 brane. So say our world volume coordinates are spatial coordinates in the direction 0 to 5. Okay? Then what we have is, for instance, this variable x6, okay, is going to be equal to x6 of x0 to x5. Right? When we write down this g alpha beta for the first 6 coordinates, it's just delta alpha beta. Okay? So we get integral square root determinant of the matrix, which is delta alpha beta, plus del alpha x6 del beta x6. And of course, similarly for the other coordinates, except in everything we're going to be doing, we're going to be maintaining the SO3 invariance under 789, which means 789 will just sit at 0.
What is this everything else?
Everything else is x7, x8 and x9.
So you're only trying to measure fluctuations along
x6. Both the D4 branes and the NS5 branes will be in configurations that preserve the SO3 symmetry of rotations in x7, x8, x9. Therefore, it's just in the origin of x7, x8, x9. So we can forget about those directions.
So then this is the only...
This is the only thing once we impose that symmetry. Okay? Good.
That is because the brain is stretching in this...
In this direction. So surely we can't preserve direction symmetry of more than this. But this configuration preserves that symmetry, and we'll keep it. Okay.
Can't have any function in that radius.
You see, the thing is that at any given point, if at any given point you have a certain direction, you're somewhere in that place. That's violating the symmetry. Any vector other than 0 in R3 is not rotationally invariant. Right? We want point-wise that symmetry to be maintained.
And here we are talking about 9 plus 1
No,
What about the 10th?
not about the 10th dimension. Not about the 10th dimension now, but we will soon talk about it when we go study M theory. And when we do that, we will have x6 and x10 to be allowed to be fluctuating. Okay, all clear? Okay. Now, suppose these fluctuations are very small. Then we can expand the determinant, using that formula involving traces. And the first correction away from the determinant of 1 will be trace of this matrix, which is whose action is basically del alpha x6, the whole thing square. Clear? The equation of motion that follows from this action is, of course, del squared x6 is equal to 0. Okay. So now let us imagine that we've got one D4 brain doing something at the origin at x6 equals 0. Whatever it's doing something. That produces some solution on the NS fiber. Except at the origin, there's no source. Where the D4 brain is, that's changing this equation. Because it's not just a free NS5 brain, it's a free NS5 brain, but something tiny.
X6 is for NS5.
What?
X6 for this action is for NS5.
The action is for NS5.
And then the source is D4.
The D4 brain is touching it, let's say at x6 equals 0. Sorry, what am I saying? It's touching it at origin in 4-5 dimension. Yeah. So let's define V is equal to x4 plus I x5. And let's say that the D4 brain is somewhere, whatever that place is, I'll call the origin. Okay, let's say that's V equals 0. There's a D4 brain there. Okay, what is the solution going to look like?
So all of this is in G string equals 0, very small.
Well, it's exactly G string equals 0, there'll be no effect of the D4 plane. This is now small effect. Okay? But you see, at infinity, you might expect everything to have decayed away. Yeah. Hang on for a minute. It's not quite correct, but we'll see. Okay? So we have some tug here. Okay? And so we look at this, the solution coming for del squared of x6 equals 0, which is spherically symmetric, rotationally symmetric around this point. But we know that that's just the Green's function in 2 dimensions. So it's log V. Okay? So we know that our solution is going to be x6 is equal to some k. I don't read. To get k, I would have to analyze how the D4 brain tugs this, times log of V. And now I'll put a V minus, let's say, A. A is the position where it tugged. Okay? This is what the impact of a D4 brain would be on this NS5 brain.
Here alpha and beta run over all the directions of the NS5.
Alpha and beta what?
0 to
Ah, yes. Yes, but once again we're preserving the symmetry in 0 to 3 directions.
All other derivatives.
Everything else. So every symmetry that is present in this thing will be preserved by solutions.
every common thing is preserved.
Every common thing that either you have brains in both or you don't have brains in both, that has a symmetry, and all our solutions are preserving it. And therefore, everything is varying only in the remaining 2 directions.
4 and 5.
What?
4 and 5. Right?
4 and 5, this V. Okay, all clear? Okay, so now we see something interesting. Because V is effectively a 2-dimensional coordinate, because we're preserving the remaining 4-dimensional symmetry. Because V is effectively a 2-dimensional coordinate, no matter how small our tug is, at infinity it can't be ignored. Because unlike if we were in 3 dimensions, where the Laplacian would go like 1 over r, here this is going to go like a log. Okay, so we see that this diagram that we drew up was a bit inaccurate. If we had one brane here, the real diagram is going to look like this. You see, as they go further and further and further away, these branes go further and further away in V, they also start going further and further away from each other in distance. Of course, this extent of bending is very small when G string is small. So if you stay in any finite region, you won't see it. If you go far enough, you will see it. Is this clear?
The G comes in K.
G comes in K. So we will find a formula for K at some point. But yeah. Okay. Excellent. Now, we're going to use this fact. Okay. And when there are many branes and everything is small, we will assume that superposition works. Okay, because the equation is linear. Okay, so the general solution will be this. Will be, suppose I've got, okay, although we're mainly going to be interested in the first part I will mainly talk about 2 branes. Let me imagine, just for generality, there was a third NS5 brane here, and I'm studying this guy. Okay, and let's say that the positions at which the 4 branes hit this guy on this side were AIs. And the positions at which 4 branes hit this on this guy, we could have 4 branes stretching from here to here as well. Let's call those BJs. Okay? Then our general solution for this brane, okay, will be that x6 will be equal to k into sum over log of mod of v minus AIs minus log of v minus BJs. This is sum over I, this is sum over j. Right, because it's intuitively clear that if a D brane from this side pulls this way, it will pull in an equal and opposite way from the other side. Okay, so this is our solution for this brane, depending on the positions and the number of 4 branes that are pulling it from the left, and the positions and number of 4 branes that are pulling it on the right. Clear? Okay. Now we're going to draw 2 immediate consequences of this. The first one is to study, okay, now remember we're going to be interested in branes that extend some finite distance here. Okay? These branes, at least locally, should be free to fluctuate their position of where they join the NS5 brane. By locally, I mean locally in 0, 1, 2, 3. The position of joining should turn out to be a field in the effective 4-dimensional theory that we will get by studying this thing. Let's understand this in a little more detail. You see,
This V is a vector.
what?
This V is a vector.
V is a complex number. A two-dimensional, just one complex number. Yeah, so like this. Because of complex numbers, a vector is what I just said clear? Yes. I said that look, we have these guys joining here, but they could instead have joined here. Where they join are different vacua of the same theory. Now, in any situation where you've got different vacua, you also have the Goldstone phenomenon, where you locally fluctuate your vacuum and get massless fields. Okay? I'm going to ask, well, really there were two. Really what I'm analyzing is this. There are two possibilities. Either these different positions are different vacua, or they're different theories. Is this clear? Okay, how do we distinguish between them? The way that they're distinguished is if they're different theories, then even their positions, even locally, cannot fluctuate. If you've got a mass, it's a mass, right? It doesn't start fluctuating as a function of x. Okay? But if you've got different vacua, then there is an associated massless field with that vacuum. The Goldstone field, which is local fluctuations in position. Okay, so I want to see whether these positions of branes are different vacua or different theories.
So this is because of the translation symmetry breaking in this type.
It's because we could have put these different branes anywhere.
Yeah, so that is translation.
Oh, in this direction. Yeah, I suppose you could say that. It's not very precisely that, because you see, this and this are not translationally related. Relative distances are not translationally related. It's because of supersymmetry. Supersymmetry is preserved no matter where you put branes, as long as you don't change their orientation. Okay? And when supersymmetry is preserved, you have an exact vacuum. So because the real answer is because of supersymmetry. You've got this degenerate set of vacua because of supersymmetry. Okay? It's a little bit like we had in the Seiberg-Witten theory. You could ask, why did you have this flat U direction? It was not coming from some broken symmetry. It was because of supersymmetry. How did we know it was not coming from broken symmetry? If it was coming from a broken symmetry, then the physics at any one point on the plane would be the same as physics at any other point. Because they'd be related by symmetry. And then there wouldn't have been a Seiberg-Witten paper, because there would be nothing to say about the U dependence of physics. Would have been trivial. The fact that we had non-trivial U dependence in physics is already telling you that didn't come from symmetry. It's going to be similar. Clear? Excellent. Okay. So we've got this. So now I'm going to try to figure out whether putting these branes at different positions are different vacua or different theories. How do I do that? Well, what I want to do is to compute the metric on the moduli space. I want to compute the kinetic term for local fluctuations of these fields. And I want to check whether they're infinite or finite. Now, how could they possibly be infinite? The forebranes are finite. So local motions in the position of the forebranes look like they'll definitely be finite. So it looks like they're vacua. However, hang on. Because the forebranes impact the fivebranes. And the fivebranes are infinite. So perhaps you could get an infinity from the impact of the position of the forebrane on the fivebrane. Is this clear? Okay. So, good. So, what we're going to do is this. We're going to imagine that these AIs, whatever they are, have some position dependence. And now try to calculate the contribution to the action of the AIs as fields in X form from the fivebrane.
So sorry, this AI was the position in this two-dimensional plane.
Yes.
Now it's a function of 0 and 2.
Exactly. So suppose AI is a function now of x mu, and bi is a function of x mu. Okay? I want to compute this action. Action I know is del mu x6. Okay? The whole thing squared. And then it has to be integrated over x4 and d2v. Because this was the action on the ns5 prime. We're computing the effect. See, the full action is the action on the whole system. We're computing the effect of changing a mu's on the action of the ns5 prime, because this is the only thing that could potentially have infinity.
You have to integrate over x4 and x5.
We have to integrate over x4 and x5 with v.
Yeah.
Okay? So we get d2v, d4x, and then whatever we get from here. Okay? So now what do we get from here? We get from here integral d2v d4x, and log, when you differentiate, becomes 1 over. Okay? We have to be careful, there's some real part and so on. None of that will matter. Roughly we get d mu of ai, d nu of aj. Okay? Let's do it one by one. D mu of ai divided by v minus ai. What? Sum over I minus d mu bj by v minus bj, and then this thing square. Clear? Okay? Now you see the following. Suppose I choose some AI fields such that sum over AI minus sum over bj, okay, is equal to 0. Meaning, here, what am I saying? What I have here is a basis of potential massless fields in my problem. I've used the fields AI and bj. But I could go to any basis I want. So suppose I first parameterize the subspace of these fields that has this property. Okay, if I do that. Now, in that case, suppose I say that, suppose there was one A and one B. I move to the field A minus B and A plus B. I'm just moving to some different field, right? Okay, but what I'm saying is that suppose, let's say, let's give some names. Suppose the number of AI fields was M and the number of BI fields was N. In fact, let's call this N1 and N2. Okay? Then I could go to, there are N1 plus N2 minus 1 fields that have this property. And then there is one field that does not. Right? So I go to a basis of fields such that this N1 plus N2 minus 1 fields are in one basket, and this other field, whatever it is, this other field is ambiguous because you can always add something from this basket to that. To say that something is not 0 doesn't fix something completely. Sorry. Hello? Okay. Nah. Okay. Fine. Is this clear? So in the space of scalar fields that we're dealing with, I can do some linear combinations to move to fields that obey this quantity. For instance, if there was one A and one B, I go to A plus B and A minus B. Okay? All of you are looking puzzled. I'll tell you why it's special. But at the moment, it's just a choice.
You're just taking some different combinations.
Some different combination of fields that happen to obey this. And you should understand that there are N1 plus N2 minus 1 such combinations. This is a linear vector space of fields whose basis is N1 plus N2 minus 1 dimension. That's clear, right? It's one condition on n1 plus n2 fields. So it's n1 plus n2 minus 1.
This I and j run over all the things like or
n1 branes
yeah.
on the left and n2 branes on the right.
Yeah.
Clear? Is this clear? Okay, excellent. Just a choice. If I do that, let's see what happens. You see, the most potentially divergent, let's go to large V. All possible divergences come from large V. At large V, this thing looks like d2V d4x. Now d4x of course is there, it's just in the 4-dimensional action, right? But the metric on moduli space is governed by d2V of sum over I d mu ai minus d mu aj bj. The whole thing squared divided by v squared. If our field is such that that combination was 0, then this term vanishes. The metric is actually given by the next term in the expansion in V. But this term is divergent. Because d2V divided by V squared is infinity as you go to take V to infinity. It's a log infinity. So, any term you get by expanding to one higher power in V will be finite. Right? Because it will have one more power of 1 over V, because we're doing a large V expansion. So it will be d2V divided by V cube, which is finite at infinity. So all such fields have massless fields. They have a finite metric on moduli space. Is this clear? However, there is one field that does not. So of these n1 plus n2 different parameters, one of them is a parameter in the Lagrangian. Okay, one of them is a parameter in the Lagrangian, and the rest are parametrizing vacua. Is this clear? Right. So at the moment what I did here was take the leading order contribution by ignoring the AI and BJ. Okay? If the leading order contribution is not 0, then that's all you care about at large V. But if it is 0, you have to go to one higher order. Okay? So then you would do this expansion here. So you take this V out, you have an AI by V, and Taylor expand in that. That'll give you an additional 1 over V. Right? So it'll be 1 over V cube. That will be finite. So whatever the metric on moduli space is for these other fields, these n1 plus n2 minus 1 fields, that is finite. So these are fluctuating fields. The positions of these branes can fluctuate locally provided they maintain the condition that sum over ai minus sum over bi is 0. Okay? However, that sum over ai minus sum over bi cannot fluctuate. Okay? That quantity will be a parameter in the Lagrangian. We will see more how that goes.
This is not a field. This one particular.
This one thing is not a field. It's fixed. It can't fluctuate.
If it fluctuates, there is a divergence. But what does it mean?
What does it mean? It means it cannot fluctuate. It stays fixed. Right?
And it's equal to 0, right?
What?
It's equal to 0.
No. Could be anything. Its derivatives have to stay.
Okay. Oh, it's a constant.
It's a constant. You put it something, it will stay that thing even locally. Therefore, it's a parameter in the Lagrangian.
So here locally means in the first 4 dimensions.
In the first 4 dimensions. We're looking at the effective quantum field theory in 4 dimensions.
AI is anyway a function of only the first 4 dimensions.
AI is anyway a function only of the first 4 dimensions. Exactly. It's an endpoint of a brain.
So the extremization principle will not allow it to fluctuate. That's what you're saying.
I'm saying that, that any fluctuation would be infinite energy.
Yeah. So it has to extremize by staying fixed.
Yeah, staying fixed.
So the condition is summation over A minus A 0 or constant?
I'm sorry, constant. I think Witten calls it QI or something, some constant.
So I see. Now it's a new variable QI of x, let's say, and then you are calculating that chain, and then you are concluding that QI is a constant.
Exactly. That QI of X would have infinite action. Yeah.
Unless QI is constant.
Unless QI is constant. So QI has to be constant. But notice that the other guys can fluctuate. A1 minus A2 could be a function of X and have finite energy. Okay? So this is the first important thing we've learned. That this logarithm at infinity has one serious consequence. It takes, of these n1 plus n2 positions, it tells us that n1 plus n2 minus one of these were fields, were vacua. Okay? But one of them was a parameter in the Lagrangian. Clear? Okay. Let's move on. Now let's look at the next consequence. By the way, if we now specialize to the theory that we will first look at, which is two NS5 branes and one of these. For any NS5 branes, there's only either an A or a B. This guy's being pulled this way, this guy's being pulled that way. So for any of the NS5 branes, the guy that does not fluctuate is sum over AI. So which means that the fluctuations can only be in those such that sum over AI is 0. Now AIs are the Coulomb branch positions. Remember that when you put four branes together, you get a UN gauge theory. Remember that when you separate the four branes, you are Higgsing this UN gauge theory. Okay? Remember that as we argued, the most general allowed Higgsing is parametrized by diagonal entries, because up to gauge transformations, every adjoint field can be diagonalized. So these diagonal entries are the positions of these four branes. Separating them Higgses UN to U1 to the power n. Okay? This discussion we could have had just in flat space without any NS5 branes. You've got some four branes, you separate them on the four brane world volume, there's UN theory. You separate them, that's Higgsing. Okay? Because now the strings stretching between one brane and the other become massive. These are the W bosons. The string stretching from one brane to the other remains massless. These are the U1 gauge fields. And you've got U1 to the power. You've Higgsed UN down to U1 to the power n. And you've done that by turning on back diagonal value for an adjoint scalar field. In fact, the diagonal values are the positions of these branes. This clear?
The complex number. They tell you the position in the 4, 5.
That's correct. In this case, in these 4, 5 directions. Right. If we were just doing D4 branes in flat space, okay, then there would have been 5 transverse dimensions, and you could have turned, the Higgsing could have been any one of these 5. Okay? But they would all have been parallel. Okay. The scalars have to commute with each other because of the potential, which is xi commutator xj, the whole thing square. The d-term potential. Okay? So the scalars cannot be independently turned on, but they can be independently turned on if they commute with each other. If they commute with each other, they're simultaneously diagonalizable. Okay? So you can turn on these branes, give them any positions you want, but they have to be commuting. Now, if you have 5 different scalars, but they all commute, 5 different adjoint scalars, but they all commute, it Higgses exactly the same way as just one scalar. Because the Higgsing is just the fact that you've made a diagonal matrix.
And what scalar is this?
The scalar is the scalar on the world volume of the D4 branes. Yeah, okay. Maybe D3 branes are more familiar. In the D3 brane, do you remember that there are 6 scalars? The vector multiplet, n equals 4 Youngmans. N equals 4 Yang-Mills theory, its field content has 2 gauge field and 6 scalar fields. These 6 scalar fields are the positions of the D3 branes in the 6 transverse dimensional space. They were actually matrices, but the branch of vacuum where you Higgs has all these matrices simultaneously commuting. Okay, so there are only positions of these branes. Is this clear? Okay, so the separation, the positions of these branes, okay, was Higgsing down the theory from UN to U1 to the power n. And had we had just infinite 4-dimensional 4 branes, the low energy theory would have been U1 to the power n. And the scalars in the vector multiplet of this U1 to the power n, of this gauge field, would have been these positions of these branes, which would then have been allowed to fluctuate. Those were the fluctuating scalars. This is clear? What we've just deduced is that one of these is not dynamical. Which is not dynamical? The one corresponding to the trace. What does that mean? It means that the theory we're getting on the world volume is not a UN theory, but an SUN theory. Okay? So, we've deduced that in this case, if you have n such branes, we should expect an SUN gauge theory. Okay, see how beautiful and physical this argument was. No complicated mathematics, simple physics gives you an interesting result. Already, we're going to see many such examples of this. Okay? Is this clear, people? Excellent. Now, let us return to another thing that we already talked about last class, but we'll look at it in more detail. Okay? The thing that we talked about at last class is we gave a classical formula for the coupling constant, the effective G3 squared Yang-Mills for these branes. And our formula was, we remembered that 1 over G squared Yang-Mills for the 4 brane was given by 1 over G, closed string coupling, times alpha prime to the what power? Well, we want 5 things to go. So times alpha. Oh no, but there was an extra alpha prime squared. Sorry, we wrote it down last time. If somebody can help me, but otherwise, p minus 3 by 2, and therefore this is just to the power half, right? Right? Yeah. Did I get that? I'll. No. This is 4 brane, 5 dimensions. Okay, and just to check, we have G squared Yang-Mills therefore is equal to alpha prime to the half G. And if we now look at the dimensionless coupling, that's alpha prime E, alpha prime to the half EG, and that correctly says that it goes to infinity at large energies, 0 at low energies, which is correct in 4 plus 1 dimensions. So correct, we got it right. We didn't get it the other way. Okay, so this was our G squared Yang-Mills 4. But the effective G squared Yang, if the length between these things was L, then the effective G squared Yang-Mills 3, you know, 3 should be thought of as 3 plus 1, okay. Maybe I should write this as 4 plus 1. Okay, is equal to L divided by G alpha to the 1/4 by dimensional reduction. Because this is what appears behind the action. And then you do the integral over L. Okay? And therefore we got the formula that G squared Yang-Mills 3 plus 1 was equal to G alpha prime to the half by L. This was the classical formula. Is this correct? Is this clear?
Why is it half? It's 1/4.
Wow, in the second column on the right.
Sorry. I don't know why I wrote. Okay, all good? Now this formula is classical. And how do we see that? We see that because there's this L here. But what does L mean? Because L, as we've just discovered, is a function of V. Okay? L is a function of V, and in fact, in a situation like this, okay? In fact, in a situation like this, at large V, L will go like 2k log V.
L is the distance between NS5 brains or the length of T4?
L is the distance between the NS5 brains. But that statement is ambiguous now. You see, when the NS5 brains were at some position, that statement made sense.
It's a function of the.
It's a function of
That two plane.
V, yes. Okay? And because this guy bends this way,
It's a
and this guy bends that way, we get this factor of 2. The two bend in opposite direction. One is pulled to the left, the other is pulled to the right.
I have one confusion.
Yes?
This coupling is the coupling of young mills in NS5 rate?
No. This coupling is the coupling of the effective coupling we see on the 3 plus 1 dimensional theory that lives on the world volume of the 4 branes. You see, on the world volume of the 4 branes, there lived a theory which was 4 plus 1 dimensional.
I'm talking about the first coupling.
First coupling was just the coupling of the 4 plus 1 dimensional coupling on the 4 branes, local 4 plus 1 dimensional coupling. Right? Locally, the physics of the 4 brane had this coupling. But now this thing is stretched over some length. We're looking at the effective 3 plus 1 dimensional coupling that you get when you integrate over this length. The action had that term, that first term out, then we integrate it over the length. Okay? If you assume nothing depends on the length, you just pull a factor of length out. So that's why you get L divided by that.
But that's the length of the D4 brane.
That's the length of the D4 brane, which is the same as the distance between the NS5 branes if you ignore all back reaction.
No, but then you're again taking that length to be the distance between the NS5 branes, right?
They're the same thing classically. Right? The D4 brane is stretching between two NS5 branes.
Classically, they are same.
Classically, it's the same thing. Quantum mechanically, we have to think. Right? The first analysis was just classical. Okay. Now, you see this length here is growing like V. Okay? In fact, there's an N here. Because Kn pulling this way, Kn pulling that way is growing like that. So if we compute, for instance, now, if we were doing some computation of, I don't know, quantum effective action, quantum effective potential, or quantum effective something, as a function of V, the effective length there would be this guy. So the effective coupling at large V would be this formula, but with L replaced by this guy.
brains are at that.
If the brains are at that position, yes, if you want to compute the effective coupling of the U1 at that position. But more generally, we could compute, for instance, are you familiar with, for instance, the Coleman-Weinberg potential, Coleman-Weinberg potential computation in phi to the 4th theory? Let me just remind you of this. This is a general feature of quantum field theory. Suppose you compute the Coleman-Weinberg potential, which is just the effective action, okay? One loop effective action, quantum effective action, compute by doing one loop diagrams in phi to the 4th theory. Okay? You get some complicated formula multiplied by G. But now, the coupling. But now you can ask, what value of the coupling should we use? Because coupling runs. And when you sum all the required diagrams, all the diagrams you should be summing the right order, not just do the one loop. It's RG corrected one loop. When you do that, what you find is that you have to use the value of G that is appropriate to your process. But what is your process? Your process is labeled only by a vacuum expectation value. Vacuum expectation value of this field has mass dimension. So you're supposed to use the coupling at that value of the mass. So if you did something similar here, even if your brains were, you did a computation at sufficiently high mass, you would have to use the RG corrected coupling constant at that mass, and this is the RG corrected coupling constant. So this is what it's really telling you. What it's really telling you is that this is the RG running of the coupling constant. But this is actually great, because we know that in 3 plus 1 dimensions, coupling constants do run logarithmically. And we can actually compute the coefficient, because in this highly supersymmetric theory, the log running is exact. The one loop running is exact. Okay? In this highly supersymmetric theory, there's no confusion. The one loop running is exact. And the beta functions are well known, and you can compare the beta functions with this answer once you figure out what k is. We'll figure that out in a bit. And we get the right answer. So this stretching of the brains is how geometry sees the beta function of these n equals 2 theories. Quite beautiful, isn't it? Very simple computation. So if Gross and Wilczek had known M theory, they would have got their calculation right like this. I mean, string theory. What? This is asymptotic. Yes. Yeah, you see that the coupling is going to 0 as V is going to infinity in this logarithmic way. Okay, but there's an issue of the number. I cannot yet tell you how the number works because we haven't yet figured out what k is. Okay, but it works. Is this clear? Okay, excellent. So this is our second qualitative payoff from this thing. We see how beautifully geometry sees this kind of running. Now, could it have been inward? Okay, no, it could not have been inward. You see, you can see this physically, because what's happening here is that this is pulling this. Okay, so it's nearest at the point where it's pulled, and then goes out. Okay?
Maybe it means negative tension or something.
Negative tension, but those don't. Yeah. Right? Okay, excellent. Excellent. Let's keep going. So now we've learned two things. In our special case, our problem is an SUN theory. First thing we've learned. Second thing, because of these IR divergence, second thing we've learned is that our problem has a beta function. Okay.
You started with this straight thing.
Yes.
And then it started pulling and then it goes
Yeah,
inside.
yes.
It's very surprising that it's going very far in the...
It's very surprising. This is the IR divergence. It's the fact that we're in 2 dimensions. In 2 dimensions, if you have just a membrane in 2 dimensions, and you pull at all on it, When you go very far away, it's got a huge effect.
And it's an exact effect, not.
Yeah, it's an exact, I mean, to the extent that the membrane is defined by del squared phi is equal to 0.
I see.
Okay? Now you may think that, look, if it's bending a lot, why is del square phi equal 0 correct?
Yeah.
Because we derived it by small fluctuations. But all we require is that it's small locally.
Yeah.
And locally it's always small. Log is very slowly varying. Okay? This is just exact. It wouldn't happen in 3 dimensions.
I mean, if you exactly solve this, you also see.
If you exactly solve it at large distances, you will see this, yes.
Can you do better prediction theory and get higher loop beta?
You cannot, because n equals to beta function is one loop exact. Okay. Okay. Excellent. You see, by the way, how much of this looks independent of supersymmetry, right? The diagrams, but behind all of it is sitting supersymmetry. You know, it's a general rule in our kind of physics that if you work with a theory that is supersymmetric enough, you can get away with murder. You can think very inaccurately and get the exact answer. How many of you were at our journal club yesterday? It made no sense, but he got the answer right. It's amazing, right? This happens all the time in these very supersymmetric theories. You know, you just try hard enough, you'll be rewarded, whether you're right or not. I've seen this many times. Your supersymmetry protects you, it's like an insurance. It protects you from normal human error. Now you have to take a superhuman effort to make an error that's so big that supersymmetry won't protect you from it. Okay. Fine. Let's keep going. So far we've done a couple of qualitative things. But now we want to get quantitative. And by the way, let me just tell you, I won't spend time on this. Let me just, since I'm not going to come back to this probably this class at least. And we're trying not to take more than at least at most 2 lectures per paper, so that we move. Let me tell you that this thing that was this sum over AI minus sum over BI, you might ask, what is the interpretation of this theory? So let me just tell you about it. Something I haven't told you at all is the following, and maybe when we study the same phenomenon in 3 dimensions, there's this famous Hanani-Witten effect that I will again come back to string theory and tell you about. Maybe then I'll explain it in more detail. But I'm just going to tell you at the moment. Suppose you've got a 5 brane, and you've got a 4 brane ending on one side, another 4 brane ending on the other. Then the string stretching between these branes, the string stretching from this brane to this, or this brane to this, are the vector multiplet here. The string stretching between this brane to this, and this brane to this, is the vector multiplet here. What about the string stretching from this brane to this brane? Those turn into hypermultiplets, matter fields. Okay? Why and how, maybe we'll come back to at a later point. Please just take it from me. Right? Okay? String stretching across branes that go across, end on one end and the other, give you matter fields, hypermultiplets. Okay? So, if you had a theory not like the one we're going to mainly study for 2 minutes just now, you had a theory like this. Some number of branes here, some number of branes here. You've got UN1 theory, UN2 theory, but you've also got hypermultiplets. You've also got some matter. This matter is in the bifundamental of these two, because there's one string stretch ending here and one ending there. Fundamental of one, anti-fundamental of the other. Okay? Now, the point is this, that when you have hypermultiplets, you can make them massive. Consistent with n equals 2 supersymmetry, you can give hypermultiplets a mass. So there should be a parameter in the problem, which is giving the hypermultiplets a mass. Now, what could that parameter be? You see, the mass of the hypermultiplet, how do you make something massive? You make something massive by separating the branes so that the string going between them has to have a lot of stretch. That's how you can make it massive. But you see, these positions of these, but there are many different positions of these branes and only one mass, because the mass is a gauge invariant quantity. The positions of these branes are not gauge invariant, right? The eigenvalues of some matrix. Positions of these branes are not gauge invariant. What is gauge invariant is the trace. So the mass is related to, not exactly given by, but it is related to the difference between positions here and the difference between positions here. The average position of these and the average position of these. But that was precisely the quantity that could not fluctuate. Sum over AI minus sum over BI. So the one parameter that was not allowed to fluctuate, we now also have an interpretation for. It is a parameter in the Lagrangian. That's why it was not allowed to fluctuate. It was the hypermultiplet mass. Is this clear? Okay. And what goes behind a lot of the remaining successes now are the following fact. See, we have identified in the low energy quantum field theory the relevant coupling, the classically marginal coupling, namely the Yang-Mills coupling, which is the size of these branes, the length between the four branes. Okay, we have identified in this thing the masses of hypermultiplets. There are no other parameters that preserve supersymmetry in this Lagrangian that are either marginal or relevant. Okay? So every other detail of the problem, once we flow to low energies, assuming that this UV picture is in the basin of attraction of this quantum field theory. So you flow to this. Every other parameter in this problem is irrelevant if it preserves supersymmetry. Because there are plenty of relevant parameters will break supersymmetry. This is part of why it's hard to go beyond supersymmetry. But if you preserve supersymmetry, every other detail will contribute to this low energy effective action in an irrelevant way. Okay? And therefore you can get away with murder. You can change things around a lot and not change your low energy physics. Just because of universality of quantum field theory. Okay? Because we've identified the only marginal and relevant parameters. Is this clear? Okay, excellent. So now that we've got all this going, let's actually try to get quantitative. So far we've just been having fun. Okay, he has this. Witten has these various digressions. Should I tell you about them? Let me tell you one of them. I get back to it. Let's get to the main point, then we come back to the digressions. Okay, main point is the solution of the model. What do I mean by that? Now we're going to go, in order to get quantitative, we're going to move away from string theory and go to M theory. Okay? And I'm going to use one fact that I have not told you about before. I'm going to use one fact that I've not told you about before. Or maybe I did at the end of the last lecture. But first, the great thing about M theory, as we've emphasized in the last lecture, is that 4 branes and 5 branes of string theory are both 5 branes of M theory. So they're going to join smoothly. We're going to get some nice kind of shape. Okay? The second thing is that in order to preserve n equals 2 supersymmetry, the world, if you've got an M theory world volume which is of the form R4 times something else, like we have here, because R4 are the 4 dimensions which we're not touching, common directions, and then we've got something else. That something else has to be a holomorphic curve. Okay? And holomorphic with some sense of complex structure. You change the complex structure, you just change which supersymmetry is preserved. if there is some complex structure with respect to which it's holomorphic, you preserve n equals 2 supersymmetry with some appropriate choice of supersymmetries. Okay? In our situation, in M theory, we have this x4 plus ix5. That gives you one complex combination. Where's the second complex combination? Exactly. We had x6, but we can do plus I x10. Okay? So this is V, and I don't know if it gives this a name. Oh, I think he calls it S. He calls it S. Let's call that S. That's a new complex variable. It has to be holomorphic in both. Okay? To preserve supersymmetry. To preserve n equals 2 supersymmetry. Okay? Great. So we've got this curve, it's got to be holomorphic. Okay. So now we've already seen that if we just looked at x6, okay, x6 had to be log, this log formula. How do we make that thing holomorphic? It's pretty clear. We just do S and we make that log V. Okay? So all of these combinations, all of these combinations, these things can be now made holomorphic. So that if you go back to the x6, it would go back to the original thing that you had. Okay? If you go back to the x6, it'll be go back to the original thing that you had. You see, one way of thinking of this is that log of mod V is the same thing as real part of log of V. Right? Because log of mod V is same as, if log of V is, take V to be mod V times e to the power I alpha. So log of V times e to the, mod V times e to the power I alpha is log of mod V plus I alpha. So the real part of log of V is same as log of mod V. We had log of mod V, now we'll write it as real part of log of V, but x6 was the real part of S. So real part of this was real part of that, holomorphic extension is, the complex numbers are equal. Is this clear? Okay. Now that we've got this picture, this formula, something interesting is sort of happening here. Okay? And that's something interesting that's happening is this. If we have S is equal to log V, okay, then let's look at the V plane and let's do a circle around it. What happens to S? Okay, the imaginary part of S makes a monodromy of 2 pi, but you might think this is inconsistent. But it's not, because the imaginary part of x was x10, which was periodic. Okay? And therefore, if we do things, normalize things correctly, let me get the normalization. Just a minute. Just 1 second, where there was some Mila here about. Here. So we will call this, we'll just put an R10 outside this. Yeah, that should. Shouldn't have needed to look, it's obvious. Right? If we have an R10 outside here, okay, then the monodromy of the imaginary part being 2 pi gives you a monodromy of 2 pi times R10 in the imaginary part of S. But we know that's also the periodicity, that's the allowed monodromy of X10. So you see that the interpretation is that now we've got an even nicer interpretation, that the end point of the vortex, end point of the forebrain is a vortex in this world volume of the NS5 brane, in the sense that X10 is winding as you go around one of these endpoints. Okay, this, by the way, completely fixes the normalization. You remember we didn't know what K was, but because it has to be periodic, of course you have to assume it's not 2 times R10, but there are independent arguments that this has vorticity 1. This completely fixes the normalization. And now you can go back from this to the string theory units. We had them yesterday. Okay? If somebody can pull out R10 in terms of G, I don't want to work it out again. Was it square root G? We can, anyway, yeah, if you could. Right, in fact, I remember. 1 by R10, which was the mass of the D0 brane, was 1 by square root alpha prime G. Okay, so R10 was order G. No, therefore this is an order G thing. This K that we claimed was small is small, and is precisely small in the right way, because the pull was because of the tension of the forebrain, which was 1 over G. The response was from the tension of the 5 brane, which was 1 over G square. So the effective response was order G. Right? So the ratio of these two dimensions got the G, exactly as we would expect. Okay, so this fact that we have this R10 here is the statement that the effect of the pull is small. It goes to 0 and the limit R10 goes to 0, which is the classical string theory limit. Is this clear? Okay, yeah, so now that we have this R10, we can figure out the exact beta function coefficients, and it works out, okay. Okay, excellent. So that was the next thing I wanted to say, that these log behaviors become holomorphic logs. But now these log behaviors were only correct at infinity. Okay? How does this 5 brane behave finitely? This is what we're now going to address. Okay, and you'll see how incredibly simple it is. What? Sorry? No, we will do things, we'll do only geometry. Just see.
Sorry, what equation you were trying to solve and what is this solution that S is equal to?
Okay, what we want to do is to find the exact shape of the 5 brane. Okay, at infinity this is what it is. But we want the exact shape.
Again, write the
Area term and minimize. But you see, that it's holomorphic already solves the minimization of the area problem.
And including extent.
What? Including extent. So we gain nothing by minimizing area, because that is automatic from the holomorphicity. All we have to do is to find a holomorphic curve that meets our boundary conditions. Holomorphicity has the equation of motion built in. Something supersymmetric solves the equation of motion automatically.
Why is it only valid at infinity?
What? No, holomorphicity is valid everywhere. No. This solution is valid at infinity because we got that by looking at just del square phi is equal to 0, which was not area minimization, it was area minimization in the limit that fluctuations were small. And that,
exact root over determinant.
we are solving that, but we will solve it without ever talking about root over determinant.
The equations that you get from solving that are the holographic.
Holomorphic. The one set of solutions of those equations is holomorphicity. There are other solutions. There are non-supersymmetric solutions to those equations.
But this one preserves supersymmetry.
This one preserves supersymmetry. It's the one we want.
We just need to find the holomorphic.
We just need to find a holomorphic curve that obeys our boundary condition.
Is this options unique?
Oh, we'll have to see. Let's see. Okay. Now, there is one nuisance in this here. And the nuisance is that x10 is periodic. Right? So, when we try to solve things in terms of S, we have to make sure that whatever we get is periodic with respect. X10 to x10 plus R comes back to the same point. How do you get rid of this nuisance? You do this in the standard way. Hey, well, let us take this variable at t is equal to e to the power s by r10. Okay? This quantity, the periodicity of s by r10, which is periodicity by 2 pi I in angle, is automatic in this quantity. So, we solve the nuisance of periodicity is removed by finding a holomorphic curve, not in the SV plane, but in the TV plane. So we work in the TV plane and look for a holomorphic curve. Okay. Now, so what is this holomorphic? Why is it a curve, by the way? It's a curve because everything is in 2 complex dimensions. And we want one condition. Okay? It's a curve because we're mathematicians, a 2-dimensional surface, right? Yes. Okay. So what are we looking for? We're looking for some function of t and v equals 0 that obeys all our boundary, that obeys everything we want.
Oh yeah.
That is a curve,
Yes.
if you're a mathematician. Right, if they were real numbers, it's clear, it's a curve. Okay. Excellent. So we're looking for f of v and t is equal to 0. Wonderful. Now, what is blow your mind amazing is how simple it is to solve this. Okay. Okay. Let us think a little bit about this curve. Okay. First, let us remember that in the classical approximation, we had v, which was suppose so let's look at this picture. We're looking for solutions that at least in some limit reduce to this picture. Okay. Now suppose I take a fixed value of x6, more precisely a fixed value of t. As I move in x6, more precisely in t, when I'm here in this classical picture, I get no solutions. When I'm here in this classical picture, I get solutions. And when I'm here in this classical picture, I get no solutions. Okay? Of course, in the quantum picture, we will find solutions even far away here, because they bend. Okay? But we put that aside for a moment. Let's look classically first. Imagine that V small, G small. Then in this region, between this and this T, we should find solutions. And the solutions are the V locations of the 4 branes. So, if we take this f of V.
So are we writing boundary conditions?
Yeah, we're trying to see what properties our f of V must satisfy. Okay, so if we take f of t naught, some fixed value, and V, and solve, Okay? If T naught is in this range, T naught in range, what exactly is going to happen outside, we're not totally sure. But at least if T naught is in this range, we should find how many solutions? N solutions. Because there should be N branes.
This N is there before or any number of things?
No, the N, we have to decide if we're trying to study SUN theory,
The UN, SUN.
then we'll have N branes. So we're trying to study SUN theory. Clear? So this is our first condition. Now let's continue to be classical and let's cut like this. Except at these very specific points, which we'll come back to. And they'll change, right? Nothing's going to be flat quantum mechanically. But except at these very special points.
Why are there n solutions? I thought one solution has position of all the n.
We are fixing some T naught and solving this equation. It will have a solution here, here, and here. How many solutions will we have for this thing? So that n looks large. Okay. Okay. On the other hand, if we do this, if we do f of t v naught, and choose, for instance, v naught to be large enough, or not something very special, how many solutions should we have? Two solutions. Yeah. A large V naught and generic V naught, right? Okay? So now, what kind of function can you think of? So let's first look at T dependence. What kind of function can you think of that has two solutions for generic V naught? Quadratic. That's pretty good. And what kind of function can you think of that has n solutions for V? Pretty good. So, so we have A of V t square plus B of V t plus C of V is equal to 0. Where A, B and V are nth order polynomials and T is T. T squares, that's it. Yeah, nothing more to say. Okay. T square is not consistent with what?
Large V P equal to E for S by R.
What is not consistent?
I thought S equal to R10 log V, and if you put that in T definition, T is just V.
Right. So you want to look at what happens at large V. Can I get? We're going to simplify this in a minute, and I'll come back to that. Hang on. Everything will be consistent. Just hang on for 2 minutes, because hang on for 2 minutes. For this, with the two more things we can say, and then it'll become simpler to answer your question. Please go on.
So, you have the two solutions are degenerate.
Yes.
What does that mean physically?
Yeah. Physically, it would mean that you would think that the coupling there is infinite, right? Because the distance between the branes has gone to 0, and that's infinite coupling. Okay, this might, it'll happen. It'll have to be some very degenerate spot for it to happen. Okay, will not generically happen. Okay, excellent. Now let's look at these polynomials and these polynomials. Already it will begin to address your questions again. Let's first look at places where CV is equal to 0. Okay? If CV is equal to 0, then at some fixed V, so suppose we have some CV and we find a V naught such that Hi, Abhijit. I'm teaching Abhijit, so you please carry on. Yeah. No, not at all. Okay. Yeah. Okay, so suppose we choose a value of V naught such that C V naught is equal to 0. And then we look at these solutions for T. We find that one of the solutions is T is equal to 0 as a solution. Right? But now let's go back to up there. T equals 0 means S is equal to minus infinity. S is equal to minus infinity was x6 equals minus infinity. S was x6 plus. Right? x6 is equal to minus infinity. So if we have something like this, then we have a solution in T, we have a brane at T equals minus, x6 equals minus infinity at that V naught. What does that mean? That means that we have a brane going like this. Because there's no way that at fixed V naught, these 5 branes can bend to infinity. 5 branes might bend to infinity, but only at infinite V. If at finite V naught, we have x6 going to infinity, that can only happen if we've got a brane not just between these two, but one extending like this as well. Actually, these are interesting systems. In these systems, because this thing is infinite, the effective coupling on this brane for the gauge theory is 0. So the gauge bosons here decouple, but the hypermultiplet that you get between these strings are still there. So this is a way of adding extra hypermultiplets to our SUN theory. You remember when we talked about the generalizations, I said one was to make it SUN, another is to add matter. This is the way we're going to add matter, but that's for later. We don't want it now. That tells us that there should be no V naught for which CV naught is 0. Then what can we say about the nature of the polynomial CV naught? It's a polynomial. It's a constant. Constant. Impossible in the complex plane for a polynomial not to have zeros. Unless it's a constant. Okay. Therefore, CV naught is a constant. So that's one simplification. Okay. Now let's look at this A guy. Suppose now we look at a situation where A V naught is equal to 0. Same conclusion. One of the solutions is T goes to infinity. Therefore, there must be a brane at x6 equals positive infinity. So if A V naught, there's some value of V naught where you go to infinity, there must be a brane like this. But we don't want that. It will be of interest later on when we want to generalize. Right now we're simple-minded people. We don't want matter. So therefore, what can we say about A? It's a constant. Okay? About B, we have nothing particular to say. About B, we have nothing particular to say. Okay? And so, what we are left with is this curve. We'll come back to Sunil's question in 2 minutes. Ct square plus B of V T plus C is equal to 0. D4 branes. Yeah, generically it does. But you know, this is now this situation, right? If you remember we said that generically it would parameterize the position of NS5 branes. But it could also be where the D4 brane, where the D brane was horizontal. But our NS5 branes are not at infinity. So if we get a solution at infinity, the only way it could be is a horizontal brane. Now, branes never stay completely horizontal, except at infinity. At infinity they straight. Then they will do whatever they do. So it's only at infinity that we could get this exactly horizontal. But that would be a deformation. Clear? Excellent. Excellent. Now, this is our final answer. But in order to see that this answer matches something we've already seen, okay, in order to see that this matches something we've already seen, okay, let us now take the special case n equals 2. Okay. So, in the special case n equals b has to be quadratic. Quadratic. Why do I think it was quadratic? B has to be quadratic. So we have at squared plus b plus some quadratic function. T plus c is equal to 0. And now why does this match? Just one second.
Now this B needs to A1 to AI and BJs, right?
Yeah. Let me do one step processing before I get to n equals 2. Sorry. Yeah. So we have v squared. Oh, he called that v. That's t squared. Yeah. Plus. Yeah. Now first I've got this a and c, but I can divide through by c. So this is 1. Then I can rescale t. So this is 1. Okay. So this thing is this. Now, what Witten does is just fool around with it. So let's take t tilde is equal to t plus b by 2. Okay. I'm just plugging this in here. Okay. So that gives me t tilde squared plus tb plus b squared by 4. Did he have a minus? So t tilde is this, and therefore I have to put t in here, so there's a minus. So minus tb. Plus tb. That was the point of making this thing, to get rid of that tb kind of thing. Plus 1 is equal to 0. Okay. So in terms of this t tilde variable, no, because it's square. T is equal to t tilde plus, minus, this is plus, t tilde minus b by 2. And now I'm substituting in here. Oh, you want the extra term here. Yeah, sorry, I did wrong. Thank you. Let me do it carefully. Sorry. So t is equal to t tilde minus b by 2. The linear terms will cancel. And the negative, let's see. So we get b squared by 4 here. Linear terms have cancelled, and then the quadratic term is minus b squared by 2. Yeah, you're right. B squared by 2, and therefore it's minus b squared by 4. Yeah. So we get minus, so t tilde squared minus b squared by 4 plus 1 is equal to 0. And therefore t tilde square is equal to b squared v by 4 minus 1. Okay, b is a degree n polynomial. Okay, b is a degree n polynomial, And therefore, we get t tilde is equal to square root of, b squared v by 4 minus 1. Now let's specialize to the case that b of v was a degree 2 polynomial. B squared is a degree 4 polynomial. Okay? So it has 4 roots. If we have 4 roots, what is the structure that we get in the square root? There's a cut between this root and this root, and there's a cut between this root and this root. So it's a double cover with 2 cuts, and so you get a torus. In fact, this is easily related to the Seiberg-Witten representation. It's just, you see, in Seiberg-Witten, we had 3, if you remember, 1, minus 1, u, but there was also a 1 at infinity. This is just, some going to stereographic coordinates and bringing infinity to a finite point. In their solution, because they were motivated by physics, the last root, meaning this weak coupling monodromy, was at infinity. But just in the theory of complex functions, you could just move that infinity to a finite point. And this is exactly that.
This argument will work in higher, so for generic n, right? So for generic n, the surface will become a genus n surface.
Exactly. So now, if we look at as Karthik said, let's suppose we were at n, at generic n. Okay, the total number of cuts will be equal to n. Well, let's see. The total number of roots was 2n. So the total number of cuts will be n. Okay, always n cuts. Okay, so as Karthik said, people have 1 cut, 2 cut, 3 cut, 4 cut. So we have n tubes joining 2 planes. That is genus n minus 1. Okay, so we get a genus G is equal to n minus 1 surface, generically. Indeed, this is what the people who analyzed the SUN generalized, Argyris and Milenkin, who generalized the Seiberg-Witten solution to SUN, found a genus n minus 1 curve. Okay, so this is our first success. Okay, we can of course want to do more. Mainly to produce the differentials on these curves. But right now we're not going to get into that. Okay? Other immediate generalizations is to add these matter fields. As we've said, we can add matter fields by adding additional d-branes here. As our analysis, as physics tells us, and then the analysis tells us that you add matter fields, you just have to change, let's say, the C to a degree k polynomial if you want k matter fields. Redo this analysis. You get what you get. Okay? Adding matter fields changes the curve in a way that is very simple. Again, matching what you expected from what people who studied it in field theory got. Then we can generalize to theories which are product gauge groups with anti-fundamental matter. Not having 2 NS right branes, but let's say 3. Then there'll be 2 gauge groups with some matter fields. There's matter fields in the bifundamental, but there could also be matter charged under 1 gauge group and the 4 branes going to infinity. Simple generalization. The generalization, if you have k NS5 branes, is instead of getting a quadratic polynomial in T, it's a degree k polynomial in T. Okay? Simple generalizations here give you all these curves. Okay?
Can you simplify this further by using that sigma AI equal to 0?
Sigma AI is equal to 0. That is automatic in this description somehow. Where does it come about in this description? Okay, good question. So let's answer that, then let's get to Sunil. The fact that we have the center of mass positions of the brains can't fluctuate. Okay, where does that come about in this description? Okay, let's ask the following. Suppose I give you an M5 brain world volume. From that, how do I deduce the effective low energy theory? My M5 brain world volume is R4 times some Riemann surface. Now I don't know anything about 4 brains and so on. But on this, there must be a low energy effective theory with some number of U1s. Where does it come from? So let's go back to that. This comes as follows. On the world volume, actually the theory of n interacting M5 brains, what that is, nobody knows. It's not even clear whether there's an answer to that question. Because in the lore, it is a non-Lagrangian theory. As I've warned you once before, that being non-Lagrangian is time dependent. So maybe there will be a nice Lagrangian description of this theory, and then we'll have an answer to what this theory is. Because, if you say there exists a theory with these properties, and you don't write it down a Lagrangian, feels, at least to people like me, extremely unsatisfying. Okay, but in the sense of what it is in the sense of Lagrangian theory, nobody knows if you have n. But if you have one 5 brain, abelian theory, well understood. Okay, the degrees of freedom on that theory include the transverse fluctuations and include the transverse fluctuations and a 3-form and a 3-form field strength or a 2-form potential. Okay, like a B mu nu kind of thing. Okay. Now, and the world volume action, apart from the area fluctuation term, also has an H mu nu rho H mu nu rho, where H is D, is the field strength of the 3-form. Okay. Now, how do you get the low energy effective action if you've got this theory? If you've got this theory on Riemann surface times R4. Basically, the idea is this. The idea is, if you choose your H to be 1-form wedge 2-form, where 2-form lives in the 4 directions, and the 1-form is one of these minimal cycles, A-type cycles on the genus G. And also, what I didn't tell you about is that this theory H was self-dual. Sorry, I should have said. It's a 2-form thing with self-dual field strength. That's one of the things that makes this M5 brain a complicated theory. Self-dual makes sense because it's a 6-dimensional theory, so 3-form can be self-dual. Is this clear? Okay. So I want to put in a configuration, but I have to solve for the self-duality constraint. Okay. So suppose I put in a configuration like this. Suppose my A-type cycles, the 1-forms dual to the A-type cycles, are alpha I, and the 1-forms dual to the B-type cycles are beta I. Okay, and I and J, alpha I intersection number with beta I is 1, and with everything else is 0. Okay, so if I put in the configuration, H is equal to alpha wedge F plus beta alpha wedge Fi plus beta beta I wedge fi star. Because alpha and beta are dual to each other, Hodge dual to each other. Okay? And f and f star are Hodge dual to each other. This configuration is automatically self-dual. I plug this into the six-dimensional action and do the integral over the two-dimensional Riemann surface. Because alpha intersection beta is 1, those go away. Okay? And what you get, of course, you could put some numbers behind this. We could put some 1 by g I square behind this. Okay. What you get is sum over 1 over I, 1 by gi squared fi wedge fi star, which is the Maxwell action. And then you can do this in a supersymmetric manner. What is the net conclusion? Net conclusion is that if you are on a genus G Riemann surface, the low energy effective, and you compactify the M5 brane on the genus G Riemann surface, the effective action has exactly G U1 gauge fields. Okay? That is n minus 1. So this description automatically has in it the fact that there were only n minus 1 gauge fields. Actually, you can ask where this came from. It came from the fact that we considered this M5 brane infinity to be compactified. Otherwise, there would have been one more one cycle you could have put at infinity. Okay? You could put one more one cycle at infinity here and infinity there. Now, the reason we did that, one way of thinking of the reason is that if you go through this analysis and you try to put one cycles there, those would give you divergent integrals. Those are not normalizable one cycles. That's another way of saying nothing can happen at infinity here, so it has to be compactified. Okay? So, once again, it's the IR that is telling you that it's n minus 1. Okay? So, but just to say that this description automatically has the n minus 1 in it.
Can't we put some sum of roots of v equal to that constant, sigma a equal to v? Because v is the coordinate where the d4 branes.
But now everything is smeared out, right?
Right, okay, in some limit. In the low energy.
That will somehow work out automatically. Yeah. There's no place where the d4 brane intersects with it.
No, because it's a
So, it's all, that picture is gone. That was an approximate picture. Now, Sunil, you had a question which we haven't answered. Let's go back to that and then let's stop the lecture.
We had S equal T.
You wanted to look at what happened at v equals infinity, right? Come. Yeah. So let's go back to okay. So let's see. So let's go back to this description. So Sunil wants to know what happens at v equals infinity. So this b of v was some quadratic thing. So v is equal to infinity. We'll just replace it by v squared. Oh, let's take the case of sun, v to the power n. Okay, so we have t squared plus v to the power n, some number which I'm not keeping track of. T plus 1 is equal to 0. Okay, and now I want to know what the roots are for this. So we have a root which is t. So because this is very large, we can balance this against this or this against this. There are two kinds of roots. One in which t is very small, the other in which t is very large. Let's look at one of them. Okay, so let's look at the the root in which t is equal to minus v to the power n. Okay? Now let's remember what t was. T was e to the power x6 plus I x10 by R10 is equal to v to the power n. Now let's take log on both sides. X6 plus I x10 is equal to n r to the power 10 log v. Exactly as we wanted. Even the n is coming out right because there were n pools. So it's meeting up that boundary condition as well. Okay, great. I think we'll stop the discussion of this paper. Witten, by the way, goes on to do a few more things. He analyzes the complicated models a little more. Let me make one comment before we stop. This is an interesting comment. Suppose I have n branes here, and I want a theory with zero beta function. What can I do? There's one very easy thing to do. Put n branes here, infinite, and n branes here. Okay? So, this theory is a theory in which it's clear that this is zero beta function, right? Because each brane has as many branes pulling it to the left as to the right, so it's not moving. Now, what is the physical description of this theory? In this theory, what we have is 2n matter multiplets. What representation are they in? Well, they're in the fundamental, really. Basically they're in the fundamental. Because you see, one of the strings is stretching to the brane, to the gauge group, and the other to some matter field. Okay? Whether this side, that side doesn't matter very much. Okay? Now, there's another way of constructing the same theory, and actually it's the equivalent construction, which is this. Suppose I take this theory with n here, and I put 2n guys here. So this guy is bent with n, but this guy is also bent with n. So though they both bend, they stay parallel to each other at infinity. So also, that's another way of saying that they have zero beta function. Sometimes it's easier to analyze in this way. Okay? So what we have concluded with zero work is that the SUN theory with 2n matter multiplets in the fundamental is a conformal field theory. Also, of course, well known, unfortunately, by the time that we wrote the paper. But this is such a simple way of seeing it. Okay? In particular, the SU2 theory with 4 matter multiplets is famously a conformal field theory for fundamental matter multiplets. So, you see, now it's famous for those who followed the field theory literature, but if you don't know it, it's just obvious for me. Okay? Yeah. So, so he has some comments, especially on these conformal field theories and so on. And then he manufactures an even larger set of field theories involving 6 branes, involving D6 branes. Okay? Let us stop this discussion here because there's no end. These constructions gone forever. Okay? Let us stop this discussion here and move on to something else next time. Let's pause for 2 minutes of questions or comments and then go for lunch.
From the spectral curve, how can we find that free potential?
Yes. So from the spectral curve, we need to do a little more work. Monodromies. We need to find, the cycles are sort of clear.
We need to find some one form.
We need to find the one forms, exactly. We need to find the one forms. Now, for mathematicians, I believe this is a very standard kind of problem. Okay, to find one forms with these.
On some.
These properties, but I haven't actually myself done this in any detail. But one of the things one can do is to look at, we've got the explicit curve. Now that we've got the curve, we can, if we want, also look and examine all the monodromies. And we take our U's and move them around. We have these things. Yeah, all that really remains is to find these one forms. Okay, the analog of the Seiberg-Witten one forms. I believe this is an entirely standard mathematical thing to do. I have not really myself.
I have just one question, is that in the spectral, that curve that we had in Seiberg-Witten
Yes.
theory was a function of u.
Yes.
So here that u goes inside this function capital B.
This U, yeah. Right.
That will depend upon that, right?
Hang on. All we have here is this torus. The U's are the parameters that enter this B. So B is a quadratic polynomial. Okay, and the parameters of that B up to things that cannot be removed by shifts and redefinitions are the U's. Because all this is the torus. Now we need a one parameter set of tori. Okay, but that you get by changing B. Okay, so the data of your moduli space is the undetermined data in this construction. When I say it's a polynomial of some degree, there's some freedom in that polynomial. Those are your vacua. Okay? Yeah, it's these shifts and so on that will change this to one complex number. These shifts and anything that cannot be absorbed by a complex redefinition, those are your real parameters. Okay? Excellent. Other questions? All that's automatic. Because we've got this torus here. Yeah, torus automatically has this SL2Z. What freedom did you talk about? Are you talking about? I think you want to know what were the monodromies. Okay? So that you can figure out. Say you take these B's and you make some loop in the space of B's. Your torus will come back when you come back, but not necessarily with the same. Those are the monodromies. The fact that this is a non-trivial fibration is that SL2Z. Okay, excellent. Other questions, comments? Okay. Last question is what should we talk about next class? Anyone has any suggestions?
You said that you talk about Ashok Sen's.
Great. Let's talk about Ashok Sen's. Let's talk about the n equals 4 theory. Sure.